Hi, everyone. Welcome to the RI seminar. Today, we have the pleasure of hearing from Stefanos Nikolaidis. Stefanos is an assistant professor in computer science at the University of Southern California. He received his PhD actually here at CMU in the Robotics Institute and a master's from MIT. He's also studied at the University of Tokyo, worked at Square Enix and the University of Washington. He was nominated for the Best Cognitive Robotics Paper Award in IROS 2019, received the Best Enabling Technologies Award at HRI 2015, was nominated for that same award HRI 2018, and was nominated for the Best Paper Award at ISR 2013, and he's received various scholarships and fellowships. I also recently learned that he's worked on an exciting problem of hairbrushing, robot hairbrushing. Unfortunately, I don't know if we'll get to see too much of that today, but I'm very excited to hear about the rest of the things that he's going to tell us about. So let's all welcome Stefanos.
Thank you very much, Dave, for the great introduction. And it's a real pleasure to be back even virtually at CMU and give this talk on robust human-robot interaction and quality diversity approach. And so I did my PhD here at CMU, where I spent probably the 4 most productive and wonderful years. You can see some familiar faces. And now I'm at the USC, where I'm an assistant professor and a directly interactive and collaborative autonomous robotic systems lab. And so when I studied at USC, what I wanted to do is I wanted to find some way to help people. And therefore, I went to a facility with post-stroke patients, and I asked them, if you have a robotic arm, like the arm on the right, what would you like the arm to help you with? And people said things like assistive eating, meal preparation, but especially one lady said, I would like the arm to help me brush my hair. And so I said, okay, let's try and see what we can do to make this work. So we started building a system where a robot has a Kinect camera and makes a model of a person's head. And then from the point cloud, we also build a mesh of the person's hair, and then the robot will follow a path, like through the person's hair, and like a constrained path. And so this worked pretty well in the lab. And then the next question was, what do we need to do to put this out and to deploy it with real users? And so, for example, one consideration when the robot moves is what happens if the user moves and the robot comes in contact with the user's skin, and how we can make sure that the robot operates in a safe manner. And so for this reason, what we did is we had a skin conductance sensor on the robot's gripper, so that when the user moves their arms upwards, the robot will emergency stop, right? So it will stop, and then therefore it will avoid contact with the skin. And so in the next part of the video, I'll show you this example, like let's say undesirable behavior. But there are many undesirable behaviors that can occur when you deploy robots to interact with real users. And so robust human-robot interaction requires identifying and accounting for undesirable behaviors. And to quote Chris Atkinson, anything can happen when we deploy robots in the wild, and we need to be able to account for a large number of failure cases. And so, the question then is how we can do that. And one approach is through user studies, and I'm a big proponent of user studies. I've spent my PhD at CMU doing user studies, and I think they're extremely important, not just for testing, but also for understanding how users may behave, and also for being able to see unexpected things that you did not expect when you build a model. But at the same time, when you have user studies, there is a limited set of user behaviors and environments that the user study can cover. And therefore, instead, what we propose is to automatically generate scenarios in simulation to better understand and test complex HRI systems. And so how can we automatically generate synthetic scenarios, and can this be helpful in finding failure cases? And as test case, we used this shared autonomy via hindsight optimization system that was developed in the personal robotics lab, where the idea behind that system is that you have a user, and the user has some goal in their mind, and the robot observes user inputs and infers the user's goal, and then attempts to assist the user in achieving that goal, for example, grasping an object. And so this is an example where the system would perform well, where you have the user, there are two objects, the user will move the joystick to the left, the user understands that the user wants to go to the left goal and helps the user by reaching that goal. And this is a very, very robust system. So we have tested this system extensively well. I remember back in the day, like the personal robotics lab, where we went to Kinova Robotics in Canada, and we had actually a person with a disability test the system. I myself have been moving objects around and try to see how the system will behave. It's a very, very robust system and can perform very well with actual users. And so what we asked is, can we generate automatically scenarios to test the system and find failures, find cases where the system may break? Now, in this case, what are scenarios? Scenarios can be joystick inputs, right? So it could be a human input sequence, and also object locations. So that is moving objects around. Now, typically, if you try to find failures, one very common approach is a single objective optimization approach, where you try to find the maximally adversarial scenario. So this scenario, for example, could occur if the user points a joystick intentionally to the wrong direction. But these global optima are easy to find. They are unlikely to occur in the real world. And so instead, what we want to do is not necessarily find a global optimum, but we want to find a diverse range of challenging scenarios. And when I was trying, so as an example, we want to find a diverse range of scenarios where, for example, the user is optimal, but also scenarios where the user is noisy. Scenarios where objects are close to each other, but scenarios where objects are far away from each other. And when I was trying to find a solution to this problem, I came of the problem on finding a diverse range of high quality solutions. I found that there is actually an entire sub-community that searches for diverse solutions that are high quality, and that's essentially the quality diversity problem. And so in single objective optimization, what you do is you typically have an objective function f that you try to maximize. In multi-objective optimization, you have, let's say, 2 or more functions, and you try to find a Pareto front. In diversity-driven search, you don't care about objectives, but you have some measures, and these measures form a space that you want to fill in. So you try to find a solution for each output combination of the measures. Quality diversity has both an objective function that you want to maximize, but also measure functions that you want to have diversity for. And so formally, we assume some objective function and some measures, which is what we want to have, which form some space that we want to cover. And so in that measure space, what we want to do is we want to find for each output combination of the measure functions, we want to find a solution so that the quality of that solution is maximized. Now the measure space is continuous, so to solve that problem, we would need infinite memory. And therefore, instead, what we do is we approximate the quality diversity objective by tessellating the space into a discrete number of cells. So we discretize the space. And the goal then becomes to find a collection of solutions so that each solution occupies a unique cell and the quality of these solutions is as high as possible. And so we try to fill in that space with solutions of as high quality as possible. And a state-of-the-art algorithm in quality diversity is MapElits, where we have a high-dimensional search space, and we map this, we search this space, but we map the space to a lower dimensional measure space. And specifically, we have an archive of solutions that we want to fill in. So we want to find a solution or a collection of solutions that fill in that space, but also we want the quality of solutions to be as high as possible. The way MapElits works is that it retains an archive with the best performance, the elites, the best solutions found. And then if it finds some solution that is better than an existing solution in an occupied cell, or if MapElits discovers a solution that finds an empty cell, then it adds that solution to the archive. Otherwise, it disregards that solution. So it tries iteratively to improve the quality of solutions on the archive and also cover the archive with solutions. And so to give some insight about how MapElits works, then we sampled some initial solutions from some fixed distribution. And then we uniformly select solutions from the archive. And then what MapElits does is it perturbs them with some isotropic Gaussian noise. And then it tries to find some new solutions. And the insight behind that is that existing solutions can act as stepping stones, where if you have a high performer in some part of the archive and you change it a little bit, then you can get some better performing or equally high performing solution in the same or some other part of the archive. So this is how map-elites works. And we said, okay, let's try to use map-elites and generate scenarios in shared autonomy and see whether we can discover failures. And the measures, which is what we wanted to have diversity for, was distance between objects. So intuitively, the more cluttered the scene, the harder the problem. And human variation. So how much the human deviates from an optimal human. And again, intuitively, the noisier the human, the worse the system would perform. And so this is a resulting archive where the y-axis is distance between objects, and the x-axis is variation. So it's like deviation from the optimal trajectory. And each cell here is generated scenario, and also its red cell here is so the color indicates a time to reach the goal, where 10 is the timeout, the maximum timeout. So red cells indicate failures. Now the quality of solutions here is whether the system fails or not. So we try to, so a high quality scenario is a scenario that challenges a shared autonomy system, right? It's a scenario where the shared autonomy system does not perform well. And so we see that we have several failures, and then let's first explore how the quality diversity algorithm behaves compared to some baselines. What this means is, can we compare the coverage of the measure space? Can we compare the number of scenarios found compared to some random search, so uniformly sampling search parameter, and also CMA-ME, which is a state-of-the-art derivative-free optimizer. And we see that indeed map-elites finds more scenarios and also more failure scenarios than CMA-ME. That's not very surprising, because CMA-ME is a single objective derivative-free optimizer. So, you know, we expect it not to have a lot of diversity with respect to the solutions found. But we also see that map-elites finds more solutions than uniformly sampling scenario parameters. Now, why this is the case? The reason behind that is what we call measure space distortion, where when we uniformly sample a high dimensional search space, it happens that in many domains, a lot of solutions are concentrated in a very small region on a lower dimensional measure space. So to give you an example, let's say that we have several objects and we uniformly sample objects on a table. The probability that all objects would be clustered on a very small region and form a cluttered scene is very, very small. The probability that all objects would be maximally distanced is also very, very small. And we can actually show that from properties of random vectors that the distances, the sample distances, are concentrated in a small region. And so even though when you do random search, even though you get a lot of diversity, you get diversity with respect not to what you actually care about, but to some scenario parameters that could be relevant. And so on the other hand, what map-elites does is specifies a measure space, and then it tries to fill in that space, which is why we find more solutions and also higher quality solutions. And we can also compute a quality diversity score, which is a score that combines the diversity and quality of solutions. And you see that the qualitative difference that that you observe in this slide between the archives can also be quantified with a quality diversity score metric, and map-elites perform better than random search in CMA-ME. Now, the next question is, how do these failures look like, and why does shared autonomy fail? So this is a case where, you know, the algorithm performs very, very well, where you have two goals, and the user points to the left, and the robot understands the user's goal. Let's examine one failure cases where human variation is high. Well, in that case, let's reproduce that case in the real world. And so what happens here is, because there is a lot of noise, there will be a jerk of the joystick to the right, and therefore the robot will get confused and go to the white distractor object. That's not very, again, surprising, in that if there is noise in human inputs, then the robot will do wrong inference, right? If the human points to the wrong object and not be able to reach the actual goal. But what was very interesting and surprising is that there were actually failure cases for a nearly optimal human. And this is an example case reproduced where the human is nearly optimal in that they move nearly straight to the goal object, which is the object in the background. However, because the shared autonomy system So the shared autonomy system runs a PAMDP and it introduces a distance-based observation function. It will get confused and it will think that the white distractor object is actually the human goal, and it will go to that object instead. And that's a very interesting case because when we were manually, when I was manually testing the system, I had not thought of actually putting the two objects one in front of the other. But it's a case that was discovered automatically from the quality diversity algorithm. And so we saw that quality diversity map elites outperforms random search and single objective optimization methods in trying to find failure scenarios. So we sent this paper to RSS and it got accepted and we were very happy about it, but reviewers pointed to two very legitimate concerns. One is that map elites still requires a very large number of evaluations to achieve good results. So I think this is actually an audience where I can appreciate the challenge that we had. We had 100 OpenRave instances running in parallel for several hours. I don't know if anyone of you still uses OpenRave, but it was quite a computationally hard experiment, right, to run. And it still requires a large number of evaluations. And the other is that the generated scenarios are still pretty simple. So we are just having a couple of objects that will move them around. And so in the next part of the talk, I will address each of the two limitations. So let's start with map elites. So the way map elites does is it selects uniformly at a given iteration solutions from the archive and perturbs them with some isotropic Gaussian noise. So this means that when applying a perturbation, map elites assume that every direction is equally promising. That's the meaning of an isotropic noise. But instead, can we generate solutions that maximize the quality diversity objective? Can we generate solutions that will help filling in the archive that will help fill in the archive? And the quality diversity objective is, to fill the archive with solutions, with as many solutions as possible, and solutions of as high quality as possible. And so, in fact, what we would like to have is we would like to have some form of a gradient of the quality diversity objective with respect to the archive. This means that we need to find some minimal perturbation of the archive, some minimum change of the archive towards maximum improvement. That's what like doing gradient ascent intuitively means, right? It's a direction of maximum improvement. Now, how can we change the archive? We can change the archive either by adding a new solution to an empty cell or by replacing an existing solution with a new, possibly better solution at an occupied cell. And so the key insight is that we formulate searching for a solution that improves the archive, and specifically for a solution that maximizes improvement as an optimization problem. We used covariance matrix adaptation evolution strategies optimizer, which what it does is it models the solutions, right? The search directions as a multivariate Gaussian, and then it samples a bunch of solutions, and then we select and rank the best solutions. So CMA selects and ranks the best solutions based on a single objective, but instead we select and rank the best solutions based on archive improvement. And then based on that, we adapt the Gaussian parameters. And we also, like CMA has also some very nice step size adaptation properties. And so therefore, what we did is we used the archiving properties of map elites, but we combined them with the selection and ranking properties of CMA-S and proposed a new algorithm called covariance matrix adaptation map elites that achieves significantly better performance in multiple benchmarks. And to test the strength of CMA-ME, of the new algorithm, we used the game domain Hearthstone. So Hearthstone is actually a very interesting game domain because you pick not only which strategy to play, but also which cards you want to have on your deck. So it's like playing chess where you don't only pick which move to make, but also which pieces you want to have on the board. And so here we use CMA-ME to search for strategies. So here to test CMA-ME, we did not search for environments, we just searched for player strategies. And so we represented the strategy as a neural network that ranks board states based on how likely they are to win the game. We did what's called neural evolution. So we optimized the neural network's parameters with CMA-ME, where the objective was to win as many games as possible. And the measures were average hand size, so how large the deck is, but also number of turns, which is how long the game will last. And so these are the two resulting archives. So where we see that CMA-ME finds more solutions, but also the solutions have lighter color, which means that they achieve a higher win rate. If you see how CMA-ME works, is it first tries to find solutions that are short. So the x-axis here is the number of terms. So it first tries to find solutions with in a small x value of the x-axis, so short solutions, and does, to some extent, good on these solutions. But then it gradually tries to find longer, to try to find some, try to play games, try to find strategies that result in longer games, and then optimize these strategies. So it's like learning how to play chess, where, in the beginning you may try fool's mate, but this can get you that far. And then over time you start playing the longer game and then become better at it. So we see that the way we define these measures, these measures for diversity, like number of turns, like how long the game will last, that's also helpful in finding a natural curriculum. And if we use the QD score, we also observe that it achieves significantly several times better performance than the state of the art. Okay, so this helped improve the performance of map elites. The second limitation that we would like to address is that the generated scenarios are simple. So can we generate more complex scenes? And one approach for more complex scenes would be to add more objects, and that will result in higher complexity. But we also care about realism. We also, if we want to test our algorithms, we want to have scenarios that are also realistic. And so, in a kitchen environment, we would like to have a pot on top of a stove and a fruit basket on top of a table, right? So there's still some human likeness that we want to preserve in the environment. And so the key insight that we propose here is latent space illumination, where we can use generative models trained with human-authored examples, and we can optimize with quality diversity algorithms, and specifically with CMA-ME, the algorithm we propose, which is very, very good in optimizing continuous spaces. We can use that to optimize the latent space of generative models to generate diverse and realistic content. As an example, DeskPad, we used here the Overcooked game domain. So in this domain here, you have two agents. Let's say that the green agent is a robot agent which runs a PAMDP, tries to infer the human subtask. The blue agent is a human which follows a rule-based model. So some heuristic model. And the goal is that the two agents need to coordinate to make a soup. So, and the idea is that they need to put some onions on the stove, and then they need to pick up a dish, pick up the soup from the stove and deliver it to the counter. And so the agents need to coordinate. And what we try to do is, can we use CMA-ME to generate overcooked environments that result in very, very diverse coordination behaviors, even if the two agents run exactly the same algorithm? So can we find diverse environments this way? And so we run CMA-ME, where we started, where the search and the search space here was the latent space of a gun. So CMA-ME would generate latent vectors that were input to a generative adversarial network, to a gun. And the gun was trained with human-authored examples, right? So the outputs match the style of training distribution, right? Match the style of the human examples. However, the outputs of a gun were had often artifacts. So what happened is that we have two agents of the same type. One, there's no pot, one path is blocked to the top. And so oftentimes the output of a gun is not an environment that is executable by the team. Therefore, what we did is we formulated generating a valid environment as a mixed integer program, where we minimize the number of edits from the output of the gun to the actual environment that we want to generate, while respecting some playability constraints. And so we formulate this as a minimum cost and network flow problem. And therefore, the output is an environment that matches the style of the human-authored examples, while being executable by the human robot team. And then we simulate the agents on this environment. We observe some coordination behaviors. We specifically measure concurrent motion, which is a team fluency metric that says for how long the agents will move. We also measure human idle time, which is how much one agent remains idle versus the other agent idle time. And then we use these metrics to update the archive. And so that we pass this as feedback to CMA-ME, which will try to find as diverse environments as possible with respect to the resulting coordination behaviors. And these are two example environments. So the left environment is an environment where the two agents coordinate very, very well. So you see that both targets, both pods are very easily accessible. So each agent can do their own thing. Now one agent will go for the dish, the other agent will infer that and adapt. And even though we have exactly the same, the agents running exactly the same algorithms, and I should say that when searching for environments, we freeze the agent policy, so we don't change the agent policies at all. We see that in this environment on the right, the coordination is much poorer. So you see that the two agents get confused. We see that one agent here has to wait for the other agent to go and pick up the divs. And this is an example environment where you see that there is a much less concurrent motion and much more idle time. And the difference comes completely from the environments and not from the agent algorithms, which are identical. And even though this environment is quite intuitive because you have a long corridor, these are all completely automatically generated environments. We can also use the same algorithm to find the corner cases. So this is an example where you have the robot, like the green agent, running a PAM-DP, and then you have the human agent, which runs some heuristics. And when they get stuck, the human agent, based on the heuristic, will do some random action. But this confuses a PAM-DP because then the belief will oscillate between two subtasks because the human goes back and forth. And so the human robot getting this like a kind of like a getting stuck dance, which is a failure case that was based on how the PAM-DP model was designed. And it was automatically discovered by the quality diversity algorithm. Now, what is exciting is that when we removed the simulated human and we had actual human users interact with a simulated robot and play the Overcooked game, we found out that in environments where team fluency was low in simulation, the amount of concurrent motion was also significantly lower than in environments where team fluency was high. And the same for idle time. So we found out that the behaviors that the diverse behaviors that we found in simulation actually translated when we used when actual users interacted with the robot agent. And so when I was like thinking of how to generate scenes and to generate environments, I thought, can we also use this to generate content for video game levels? And actually, before coming to CMU, and before coming to the States, I worked as a game engine developer at the Square Enix video game company in Japan. And so at that time, what we did was we were making tools for designers. And what we quickly found out is that the tools that we made that were very carefully optimized were never used by the designers, but they were used as a starting point for design exploration. So designers needed to have a lot of different options that they can use to further explore, rather than being given the final answer from us. And so I said, okay, can we use exactly the same pipeline to generate diverse video game levels? So we had several human-authored, human-designed video game levels, and then we trained a GAN, a generative adversarial network, and then we had a simulated agent, an A-star agent, play the level and evaluate the level based on how fair the agent got. But we said, instead of trying to generate one level, can we generate an archive of levels that are diverse with respect to the number of enemies and the number of tiles in the sky, so the number of tiles that are high up. And so this is an example generated level with a very large number of enemies and a small number of tiles in the sky. This is an example level with no sky tiles, but only in a very large number of enemies. This is the opposite, so very small number of enemies, but a lot of sky tiles. And this is somewhere in between. And what is important is that all this archive of video game levels was generated from a single run of CMA-ME exploring the latent space of a generative adversarial network. Okay, so this shows how we can use quality diversity to search a continuous space and also to generate content in scenarios that are much more complex, but also match the style of human examples. I wanted to come back to the first part where we say that, on how to search the scenario space. And in all the algorithms that we have discussed, both MapElite and CMA-ME treat the objective and measure function as black boxes. So they don't assume any grading information whatsoever. But there are actually many applications where you can have access to the gradient, both of the objective and the measures. And so we define this the differentiable quality diversity problem, where both the objectives and measures are first order differentiable. What is an application that would match this definition? So one is the style gun and clip pipeline, where you have a latent vector and you pass it to a style gun, and then you generate an image. And then you also have a text prompt that says Elon Musk with short hair. And you pass these two as inputs to a clip model trained by OpenAI, which will give you a score. Now, all this pipeline is end-to-end differentiable. So what you can do is you can do gradient ascent and find images that look as closely to Elon Musk with short hair as possible. But how about generating a range of images that look like Elon but are diverse with respect to, for example, hair color and eye color? To do that, one approach would be to use exactly the same pipeline where you specify some text prompt that says a man with blue eyes, and then you get a similarity score from clip model that tells you how much the image matches a test score. But then instead of trying to optimize to do gradient ascent of that, you try to just find images for a range of scores that where Elon Musk has blue eyes but also has different eye color. And what is interesting is that even then, in this example now, even the measure is also end-to-end differentiable. And so then the question becomes, what happens when both the objective and the measures are end-to-end differentiable? And this means that we have exact gradient information of the measures. And how we leverage this information in quality diversity has been an open problem for several years. And we solved that problem. And so in the next slides, I will give you the intuition on how we did that. And so what MapElits does is it takes a solution and uses some isotropic Gaussian noise to update the solution, right? So it assumes every direction is equally likely. Can we leverage gradient information? Now, if we just try to optimize an objective and we know the gradient, then we can just do gradient ascent. It's not very hard. But remember that what we care about is a quality diversity objective, which is not just maximize an objective function, but also fill in a space specified by measure functions. And so the question then becomes, how do we exploit the gradient to fill in, to cover the measure space? Now, let's assume that we have two measures, M1 and M2. The gradient of M1 with respect to theta is a direction of steepest ascent with respect to M1. The gradient of M2, the same, direction of steepest ascent with respect to M2. And the negative gradients are the directions of steepest descent. And so we see that the gradients here form some sort of a coordinate system. And therefore, if we multiply some scalar values with the gradients, we can perform some motion in this coordinate system. So we can perform some motion in measure space. And so while we're for a single objective, we can follow the direction of gradient ascent. When we have measures, we don't want to do that because we don't want to just maximize the measures. Remember that we want to find solutions for every output combination of measure functions. So we want to branch like a tree. So we want to have some kind of branching tree structure, but there is still a directionality in the search in that we still want to maximize the objective. And so we borrow the term arborescence from graph theory to indicate that we have a directed tree search. And so before, when we did, what MapElits would do is we take a solution and then isotropically perturb it. Here, what we will do is we will define a function g that is a linear combination of the objective and measures. And so maximizing g results in maximizing the objective and performing some motion on the measure space, in the measure space. And we will do a gradient ascent on g. Now, the next question is, how do we pick these coefficients that define which direction we move and how much we move? And one approach would be to sample the coefficients from a multivariate Gaussian. But what we found out that actually works much better is to search for the coefficients to maximize archive improvement. And so we will use the same insight as before, but before we search for solutions that maximize archive improvement, here we search for coefficients that specify a gradient ascent direction where moving in that direction will maximize archive improvement. And so we will have a population of coefficients, we select and rank the coefficients based on how much they improve, based on how much a gradient a step on each coefficient will improve the archive, and then update the parameters and also still leverage the nice step size adaptation properties from CMA-ME. And so this is the covariance matrix adaptation map elix via gradient arborescence algorithm, which we presented as an oral presentation at NeurIPS this year, where the idea is you have a multivariate Gaussian with your sample coefficients from this Gaussian, and then you branch from in objective measure gradient space, and then you evaluate the solution that results from every branch. You use them to update the archive, and then you pick the most promising direction and do a gradient ascent step. But also you use the ranking of the solutions to adapt the multivariate Gaussian so that you can pick better coefficients in the next iteration. And so to give some intuition on why this works, imagine that you have a three-dimensional search space. So imagine that you are like in a room, and then you have, let's say, one measure and one objective, right? So you have a two-dimensional objective measure space. So then the two-dimensional objective measure space will be a sheet in the room. And then what you do is within the surface of that sheet, you are searching for the best promising direction to do gradient ascent. And then you do one step, and then you recompute the gradients. So now the sheet has moved. So the optimization landscape has moved a little bit. And then you do this again iteratively. You compute you make a gradient step again, and so on. And so this is a visualization of the gradient arborescence, projected arborescence, projected in measure space. And we were able, for the first time, to completely solve some benchmark domains. So you see how like CMA-Mega performs compared to the state-of-the-art algorithms, including CMA-ME. And to come back to the original motivating application, we try to find diverse images of Elon Musk. So this is a example images generated from one run of CMA-Mega, where as you move down as you move down, then you see that the hair color becomes more and more red. And as you move to the left, you see that the eye color becomes more and more blue. And like what the X and Y axis values are the clip similarity score. And these are two cherry-picked examples. This is Beyonce. So as she goes down, she becomes younger, and she moves to the left. Her hair becomes longer. And one cherry-picked example again. And so this is also an example of Jennifer Lopez, where as we go down, she becomes frowning. As we go to the left, her hair becomes longer. Now, all these examples and all these algorithms that I have discussed, we have open sourced them in a library called PyRips. And we have also several tutorials. So one example tutorial is a lunar lander. So a standard way to land is like vertically, but with quality diversity. You can make the lunar lander land like a space shuttle, so you can see how quality diversity algorithms can find diverse high quality strategies in many benchmark domains. One application that I have been interested in since the beginning of my PhD studies has been learning human preferences. So this is an example where even though there is a near infinite number of possible action sequences that a human and robot can do, we found out that people can actually be clustered in a small set of dominant types or preferences. So we can learn a low-dimensional representation of human preferences. And therefore, a robot, when a new user comes, a robot can very efficiently infer what the user type or preference is and adapt to that user. And we have extended this to a more complex task, but we found out that in actual tasks like this IKEA assembly task, human preferences exist in multiple resolutions. And so, for example, in this example here, the people have different preference both on whether to assemble the shelves first or the boards first, but also then people were grouped into subgroups, had dominant preferences in subgroups on how to connect the cells to the board. And so leveraging that kind of like multi-resolution clustering of human preferences resulted in improvements in performance. And now we are extending this work to a much more complex task of model airplane assembly that involves also a mobile manipulator. So we have, this is a project funded by NSF NRI, and we have a bunch of model airplanes that students use for experiments, and students only use these airplanes for the experiments and never fly them around. Wink, wink. When learning from human demonstrations, many of these demonstrations are imperfect or suboptimal. So what we have also been looking at is how we can extract useful information even from imperfect demonstrations. And I would like to come back to the hair brushing example that I mentioned in the beginning of the talk, and we have actually been working a lot on iterating and making this more and more robust. So back then, when conferences were still in person, we did a live demonstration with a robotic arm. And this is Nathan. He has short hair, and the robot immediately finds his hair mesh and moves through a constrained path. But Yura, who was an undergrad with us through the summer, she has much longer hair, so the robot needs to adapt its motion to follow her hairstyle. And another application that we have been looking at is robot-assisted roof bolting. So this is an example of roof bolting operation where the human places a drill on the roof bolter, and then the roof bolter will go and drill the ceiling, and then the human will insert a steel bolt to reinforce the ceiling. And this is a very dangerous operation, and if something goes wrong with hair combing, it will hurt a little bit. But this roof bolter runs on hydraulics, so if something goes wrong, there will be, it's not going to stop. There will be severe injury or death. And so what we have been doing in collaboration with the mining department at the mining engineering department at the University of Kentucky is we have been having a human specify high level goals to a robotic manipulator, which then interfaces with a roof bolter to do the task safely. So we remove the human from the danger zone while still allowing the human some control of the robotic arm. I also wanted to mention that, since I started at USC, when I introduced a new robotics class with 5 Kinova arms. And so what we teach is the manipulation and planning pipeline, and students have the chance to completely implement this pipeline from scratch on the actual robotic arms. And last year, everything was done in simulation, but fortunately this year we had the chance to do this in person. This is the most important slide. So these are the students that did all the work. So Matthew Fontaine has been working on quality diversity optimization, scenario generation for human-robot interaction, and latent space illumination. Sophie Su, Yulun Zhang, and Brian Chanaka have been working on environment generation that result in diverse coordination behaviors. Brian Chanaka has also been leading the development of the open source PyRibs library. Herab Nemlekar on learning from human preferences in assembly tasks. Anirudh Puranik on learning from imperfect demonstrations, Nathan Denler on the hair combing project, and Kejia Zhang on the roof bolting project. I would also like to thank my wonderful mentors and collaborators. And the main takeaway that I wanted you to have from this talk is that there are many applications, including scenario generation and human-robot interaction, where we actually want to find a diverse range of high-quality solutions. And we talked about how to efficiently search the space, the continuous space of scenarios with quality diversity algorithms, but also how to integrate quality diversity algorithms with generative models so that we can generate diverse and realistic content. And with that, I would be happy to take any questions.
Great. Let's all thank the speaker. Yeah, for a really nice talk. Sure. Great. So yeah, everyone should feel free to raise your hand if you have a question, and then we can call on you to ask your question. While people are thinking, I'll start off with one. So I was wondering if you thought about how quality diversity could be used for adaptation to unforeseen circumstances. So if we sort of plan ahead many different strategies and then try one strategy and it fails, can we then switch to a different strategy on the fly? Is that something that you've explored or?
Yeah, absolutely. And in fact, one of the first quality diversity papers, MAP-Elites, was focused on adaptation, right? So the way to use quality diversity algorithms for adaptation would be the following. You do the quality diversity search in simulation, but you don't really know very well like what the performance will be, right? Because it's simulation. And so what you do is you have a prior, so with low confidence, and then you try it on the real world, and then you get some evidence. And then you can do this iteratively. So you can essentially model the objective function, right? That the performance is a Gaussian process. And then you could do some form of Bayesian optimization. This is what was done in the original MAP-Elites paper, where they were able to find out in like very, very small number of iterations, like to adapt to, for example, unforeseen circumstances or like robot damage. So this is an example like through trial and error with that you can, and you can use it, you can do the same thing with scenarios too, right? So you can have like you can do scenario generation and see how the scenario pans out in the real world, and then adapt what you consider as objective function and measures of a given scenario. So how hard the scenario is, or what are the performance metrics in that scenario. You can adapt it online through interaction with the real world.
Right, that makes sense. I think Zachary has a question.
Hi, Stefanos. Nice talk.
Oh,
Thank you. So I was wondering about so you're showing, CMA-ME and MAP-Elites. It looks like it still needs a lot of samples to learn. And so you've been using simulation, which totally makes sense. But one of the things I've been recognizing recently, and sadly it seems to still be the case, is that in a lot of HRI contexts, at least, simulation isn't widely accessible. Especially when you're interacting with real people, there aren't really great simulation environments yet. And so what's the gap there, right? Can we take these MAP-Elites or CMA-ME and apply them to environments where with real people where we can't collect 10,000 simulation samples? Do we always need a simulator? Do we just need better simulators of people?
Right. No, I think that's a great point, and obviously a point that I've been thinking a lot. So I think there's a number of considerations, and so one is that well, how do we model humans? And so for me, I think the way that seems to be better is to have some low fidelity simulation where you don't try exactly to model every motion of the human arm, right? And because that can actually be different, like when you interact with actual users in the real world. But you can start by thinking, as a first step, you can start by thinking how people change the objects in the world, in the physical world, and try to simulate that. And then you can get arbitrarily complex on like how people reason about task actions, right? You can use like bounded rational models. You can use imitation learning. So that would be the first step. At the same time, though, my understanding is that this would be more like an iterative process where you don't. Right. It's an iterative process where you first search for scenarios and then you find failure cases and then you try them on the real world, and this can actually inform further studies, right? And that is like a feedback loop that then, and the further studies can then inform future scenario testing. And so for example, right, what we found is that in the beginning we try to move objects around, and we thought that distance between objects matters, but then we found that actually the relative angle from the robots and effector to the objects is even more important, right? So that's something that we discovered by searching for a specific type of failure cases that would inform future work. What is interesting is that you don't need to have a very accurate model of people to discover interesting failure cases. So for example, in the Overcooked game, the simulated human was using a very simple rule-based human model. It was like just a set of if then else statement. When we removed the human, we had actual users. Obviously, like their model is different, perhaps substantially, but we saw that the differences we saw in like the generative environments that were low influency and high influency were still translated to real world. So there wasn't, of course, an exact match of like how the simulation measures. There wasn't exact match of like amount of concurrent motion between simulation and real world, but there was a strong correlation between harder environments and simpler environments, right? So I see this as an iterative process between testing things. And the argument that I want to make is that one thing that I have been doing in the past, was when to test things, I would just like randomly generate environments or randomly sample actions or have some like simple rational human model. But we can do much better when we try to test things before running a user study or deploying things in the real world.
Cool. Thank you.